Hey guys, and welcome to the first part of my new series, which deals with regularization methods. Regularization methods are a huge class of numeric algorithms which are used in optimal control and in inverse problems. And I want to give you some insight into these methods. Hi, my name is Frank, and welcome on this channel. Before we start to define optimal control in inverse problems, we have to start very basic and introduce the so-called forward problem. Assume that you have given a bunch of data which is symbolized by these pieces of paper here, and you have a black box which processes these data and produces some output. You can see this schema here. You have the input, which goes into the black box, and out comes the output. We want to give them some names. So the input is called the input, of course, and the output is called the output because it's the output. But sometimes the input is called the control because it actually controls the black box. And the state is sometimes called, the output is sometimes called the state because this is something you can observe. This is the state of your physical system you want to optimize. The black box can be anything you want it to be. For instance, it can be a partial differential equation, it can be an ordinary differential equation, or if you go a little bit more into medical imaging, it can be, for instance, a Fourier transformation. I want to make a small remark. A couple of months ago, I did a video about the optimal control of the double pendulum, which is modeled by an ordinary differential equation. You can find the link in the description. And if you're interested in this, I recommend you this video. Why is this process now called forward problem? Some people say because it's straightforward to compute. I've never heard this joke before, but it will be made clearer on the next slide. We now try to reverse this process. What do I mean with reverse this process or the inverse problem of this? Well, imagine that you are given a certain state, a certain output. And you ask yourself, well, how does the associated input look like? If I put this input inside a black box, I get exactly my desired or my given output. This, in fact, is a very tricky question. And now it's clear why it's called forward problem and inverse problem, because for every given input, I just plug the input inside a black box and out comes the output. This always works. However, it's not clear, or it's not exactly clear how do I get the associated input for every output. This is very tricky. You can say, okay, well, just put the output in inverse of the black box, and you get the desired input. Well, this is correct if the inverse of the black box exists. And does it exist? Well, if the question is asked in that specific way, the answer is of course no. The inverse does not always exist, and this is exactly why I made this video, or why this huge area of inverse problems actually exists. And in the following, I will present you a physical system where it's quite clear that the inverse does not always exist. The task is to reconstruct a two-dimensional object just by using its shadows. What does this mean? Assume you have given following physical system. On the left-hand side, we have a light source, for instance, a torchlight here. And on the right-hand side, we have a detector, which measures the light intensity of the light emitted by our light source. And here in the middle, we will place our test object. Here, our test object for now is an ellipse. And if our light source now emits light, and the ray of light is blocked by the test object, well, the light intensity detector will measure 0. Let's fire up our light source. There you go. You see the light source emit rays of light, and where the beams of light fall on our light intensity detector, for instance, it is 100% intensity, while if the light is blocked by our test object, the intensity is 0. And you can already see it here. We now start to rotate our object to get shadows in relation to the rotation. Assume that our test object is fixed here in the middle, and now we are trying to rotate it. Let's rotate our object, for instance, by 90 degrees. There you go. Now most parts of the light emitted are blocked by our test object, so a great or a major part of our light intensity detector will measure 0. You can do this now for every angle, and the result can be plotted into a 2D plot where the x-axis is the rotation angle and the y-axis is the intensity measured by our light intensity detector. This, for instance, may look like this. So here we have the plot. On the x-axis, as I said, we have the rotation angle, and on the y-axis we have our measurement of our light intensity detector. You can see here we started with rotation angle 0, where just a small part of our detector is blocked by our test object. So the gray part here is where our measurement is 0, while the white part here is where our measurement is, for instance, 100% or 1. And now we start rotating, slowly rotating. More and more light is blocked by our test object until we reached 90 degrees. At 90 degrees, of course, this is the where the most part of our detector is blocked by our test object. And you can see here, this is the measurement here at the x point 90 degrees. And then again, you can start rotating and you will come back to a very small region of the light detector blocked, and then you increase it again and so on. And this is something now you will observe. You don't know the test object, but you only know its shadows or the state of or the measurement of our light intensity detector. And now it's clear why it's called state, because this is the output of our physical system. We do not know the structure of the object, we just know the measurement of the light detector or how much light is blocked by our test object. What is the forward problem here and what is the inverse problem here? Well, let's start with the black box. The black box is of course our physical system with the light source here and the light intensity detector, and we rotate our object here. This is our black box. And now we can define our forward problem. Our forward problem, now the input for our forward problem is our two-dimensional test object, which is now plugged into our black box, which then computes for every angle the light intensity detector measurement and gives the 2D output plot, which you can see here. This is our forward problem. So again, the forward problem gets a two-dimensional object and outputs the light intensity detector measurement. On the other hand, now the inverse problem, well, it's the other way around. We are given a measurement for certain angles of our light intensity detector, and our task is now, well, how does the associated test object may have looked like? And this is, of course, a very tricky and not so easy to be answered question. But we can answer one question, namely, does the inverse of our black box exist? And to answer this question, I want to present you two objects, object number 1 and object number 2. And now put these two objects into our black box, into our physical system, and start rotating it and imagine what does the light intensity detector measures. And you see that both objects have the same output. Well, and this shows that the black box is not injective and therefore cannot be directly or cannot be inverted. And you see that in reality, we have a lot of issues because, well, which of those two objects is the correct one? You don't know, you cannot tell. And this is something we have to take care in our modeling process. Of course, this example is mainly used for educational purposes, of course, but it gives you a certain understanding of what is a forward problem and what is an inverse problem, and what are the difficulties when solving one of them. And in fact, This problem is not so far from reality as you may have thought. Imagine that you have given some satellite photos of some structures out there in the wild. Structures throw shadows, and if you know where the sun is located at the time where the photo is taken, then you can reconstruct the three-dimensional structure of this object using the satellite data. So this is a nice application of this shape reconstruction if you only have shadows available. Another huge, and I mean very huge, area of inverse problems is the medical image reconstruction. For instance, in computerized tomography, there are beams of high energy are shot through your body, and you measure the energy loss. The higher the density of the passing material in your body, the higher the loss, the higher the energy loss. And you can measure this energy loss. And now you keep rotating these light emitting or these energy beams emitting structure around your body. Of course, not you are rotated, but rather the machinery around you. You can reconstruct the bones in your body because bones have a higher density than flesh, for instance, and a higher density means a higher energy absorption. And this is enough to reconstruct the three-dimensional structure of bones in your body, for instance. This is, for instance, modeled by a Fourier transformation. I just mentioned this in the very beginning of the video. Of course, you can put this on another level if you want to reconstruct the blood vessels in your body. And, well, medical imaging is a huge part. It's a huge part. And a lot of research, and a lot of money, and a lot of energy, and a lot of good people work in this area. And of course, I can imagine that this is very useful if you can look inside the body without actually opening it. Right? This is the idea behind medical image reconstruction. Another example of inverse problems is the optimal control of fluid or gases. Here we can see the Stellarator design, which is used in the Wendelstein 7X, which is an experimental fusion power in Germany. Where is there an inverse problem? Well, one of the tasks was to control the plasma, so the yellow part here is the plasma, in such a way, it should be controlled in such a way such that it does not touch its surroundings, because if it touches its surroundings, the fusion process immediately collapses. So they had to build these blue things here, which are super magnets, which control the fluid. And you have them designed in such a way that a lot of physical properties are satisfied. That's where this super weird design comes from. This comes from an optimal control problem or an inverse problem. And this is, of course, a very sophisticated design. So that's where this is, for instance, another application of an inverse problem. So we did a lot of talking how and where we can find inverse problems in our everyday lives and in reality, but how do they actually look like from a mathematical point of view? So now we start very easy and assume that A is an operator going from a set U going to a set Y. And we assume that A is now our black box. A models our black box. Then we say that the forward problem is simply have some initial data, apply our operator, and obtain our state or our output Y. So this is just definition of a forward problem. In the inverse problem, of course, we have to do a little bit more, because we already know that the inverse problem, or that the operator A is not invertible, or it's not always invertible. So we cannot just simply apply A minus 1 or A inverse to Y and obtain U. This is not possible. But we can find a solution as close as possible. What does it mean? Assume that we are given a certain state Y. This is given, this is the output, or this is the state of our system, this is given. And we want to find a control U, so an input data U, such that our black box is as close as possible to the state Y if we apply it to U. So we want to minimize the following optimization problem. we want to steer our system A applied to U as close as possible to Y in some certain norm. This, of course, is then modeled by an optimization problem. And as I said, inverse problems and optimal control problems are very, very related. In the end, both are optimization problems, in a certain way, of course. We now need some work done by Hadamard. Hadamard was a mathematician who lived from the middle of the 19th to the middle of the 20th century. And he has made major contribution to, for instance, differential geometry and partial differential equations. And most important for us, he made the definition of well-posedness. So when is a problem well-posed? Well, it must satisfy the following three conditions. You can see them here. Number one, a solution exists. Okay, this is kind of clear. If a problem does not have a solution, it is not good in a certain way. Number two, which is a little bit stronger, the solution must be unique. This is a little bit more because, well, an optimal control problem can have more than one solutions, but to be well posed, it must be unique. So number one and number two are actually quite clear. Number three is not so easy to understood. It says the solution's behavior changes continuously with the initial conditions. This is something tricky, but it actually is needed for our numerical methods in order to be stable. We will see this in a moment. What does this mean? And of course, we say that a problem is ill-posed if it's not well-posed. Well, this is kind of clear. What does this definition mean to our inverse problems? Well, let's take a look at the following general optimization problem. We want to minimize the following expression: A applied to A as operator applied to U minus Y in some norm squared. In addition, we assume that our control U lies in a certain set U ad, so ad stands for admissible here. In order to be well posed, this optimization problem must satisfy the three conditions. Number one, a solution exists, meaning for every given Y, every given state Y, there exists a solution in our admissible set such that U solves the optimization problem here. Number two, of course, the solution is unique. And number three, we said the solution depends continuously on the initial condition or with the initial conditions. What does this mean in our case? That means that we are given two different states Y. So Y1, Y2, and we know that for every state Y1 and state Y2 plugged in here in the optimization problem, there exists a unique solution which is called bar U1 and bar U2. And we now say, or we say that the solution depends continuously with the initial conditions if the difference between the control, so the solution of an optimization problem, U1 bar minus U2 bar in a norm, is less or equal than a constant multiplied by the difference between our given states. But we want the constant C to be independent from Y. So this means that the solution depends continuously on the initial condition. Or in other way, if you put it in another word, if Y2 is a small perturbation of our state Y1, the solution the associated solution of the disturbed problem is not that far away from our solution U1. It's just limited by our constant C, but this is independent. This mainly just depends on the optimization problem itself and the difference between our states. So this is the perturbation. This is the interpretation of the solution depends continuously with the initial condition. We want our solution to be stable with respect to perturbations. Next, we want to consider a problem which is ill-posed, hence not well-posed, and to do so, we violate property number 3 of well-posedness, namely that the solution depends continuously on the initial data. To do so, consider the following optimization problem, which is actually quite easy. We want to minimize u and y over the objective function y j of y, which is just the difference y minus z, where z is a given state. The constraint we want to take a look at is the heat equation. So nothing special here. Of course, or it's very clear that a couple bar u bar y is a solution if the objective function is 0. Or in other words, if bar y is z. If we plug this into our heat equation, we know that in this case bar u must equal mainly the second derivative, the negative second derivative of z. And this now gives us the opportunity or the possibility to construct solutions where number 3 of the definition of well-posedness is violated. Set omega to be the interval from 0 to pi and delta just 1 over k. So if k goes to infinity, delta goes to 0. Our initial data, z1 and z2, is set to be 0 or delta times sinus x over delta. So if delta goes to 0, the frequency goes to 0 and the amplitude goes to 0. We just checked that the optimal solutions or the solutions for this given input u1 and u2 are just the second negative derivative, which happens to be 0 and 1 over delta times sinus x over delta. So let's take a look at u2 and z2. Here we had that the amplitude goes to 0, while here the amplitude goes to infinity. And this will now show us that number 3 is violated. Of course, but this is just very easy to check, that the couple u1 and z1 and u2 and z2 are indeed solutions to our optimization problem. But this is just straightforward. So, talking about straightforward calculations, we now compute the differences in the L2 norm. So z1 minus z2 in the L2 norm is less or equal than pi times delta. And a little bit more complicated, I just skipped the calculations here. But most important, we see that the difference of z1 minus z2 is bounded by above by delta, while the difference u1 minus u2 is bounded from below by delta, by 1 over delta. And this gives us a violation to our property number 3, because if this problem would be well posed, there would be a constant such that u1 minus u2 is less or equal than z times z1 minus z2. But we just saw that this can be estimated by above by delta, or by delta squared in this case, and from below by 1 over delta squared. Well, if you now put delta to be small enough, or k big enough, and I'm putting in other words, this is of course a contradiction. And this shows that small perturbations of order delta in our initial data, which you can see here, lead to a perturbation of order 1 over delta in the solution, which you can see here, this estimation here. And this, of course, violates the definition of well-posedness in the sense of Hadamard, because this is not stable with respect to perturbations. How does the solutions look like? Well, we can take a look at the plot. Very easy. On the left-hand side, you have the control. On the right-hand side, you have the state. And it's plotted for different values of k, namely 1, 5, and 15. And you can see if we increase k, the control becomes more and more oscillating. So the amplitude is going to infinity while the frequency is going to 0. On the other hand, the state, there also the frequency goes to infinity, but the amplitude is going to 0. And this does not work in the sense of Hadamard, because a small sinusoidal perturbations, and this is nothing more than a sinusoidal perturbation, should also lead to a small perturbation in the control, but the error in the control is going to infinity. And this is, well, not well posed. Why is this so important? Well, if you're starting to discretize, for instance, your optimization problem, you always have small perturbations. This is coming from a discretization. And this discretization perturbation, or this error coming from a perturbation, may lead to a complete different solution, as you would have expected in the non-discretized version. This is a huge problem. On the other hand, if you go to real-world applications, you always have small perturbations in your desired state coming from measurement elements or whatever reasons. You never have exact data. And therefore, we need well-posedness in order to guarantee that our problem becomes stable in the presence of perturbations. How do we do this? Well, this is part of the next videos. I will stop here right now. I've talked enough for this video. In the next video, I will show you some algorithms or some techniques how we can transform this ill-posed problem into well-posed problems and actually how to solve them. I hope you enjoyed this video so far. I hope you're curious for the next videos, and I hope to see you in the next videos. Have fun, see you around, and cheers!